All right, I picked a great time to stop because now for part 2 of this, we're about to talk about method 2. And method 2 is different because they give us this statement of a ds. So again, if you compare, here they gave us just this information we're supposed to integrate. Well, let's find a different one. We're supposed to integrate, I've scribbled all over these things. And we're given a path, and we're just given a vector valued function here. But again, the way it's presented in this particular situation is that I see that I have this ds, and so that's why I need to do something just a tad different for this. So I just want to make sure that you're aware it's a little bit different. Anyway, so we're supposed to go from this point to this point, and it's just another line segment again. So we find the vector, which is easy, 4 minus 0 and 6 minus 3. And if we're using this point, again, it's going to be from 0 to 1 when we do this. And that's why your boundary is going to be this. And this is just the equation of the line segment like we talked about before. So even though they write the ds, I want to pause it a second. Alright, my memory failed me. Can you believe it? This is still method 1. So it is not method 2. It is still method 1. And they just have presented it this way with the ds, which makes it look a little bit different. But the process is the same. We have to get our vector valued function, which is this right here. We have to take the derivative. We have to do the magnitude of the velocity. And that's where the 5 dt comes from. So that's your change in arc length, ds. And we just have to convert this function based upon what x is and what y is, and it's pretty obvious here and here what x and y is. So you have 4t for this and sine of 3t plus 3 for that. And you can multiply some numbers and you have 20. And then all of my Calc 2 students should sweat if I didn't have the problem there right in front of you. But this is going to be a tabular integration by parts. And anybody that didn't take Calc 2 with me and don't know this, shame on their Calc 2 teacher. But hopefully everybody does it around this place these days. So anyway, the way I do it is I call this an f of t. Let's just do a different color here. This is my f of t, and this is my g of t that I have to get by taking an antiderivative with respect to t. I just don't show all this extra notation each time. So I have to take the derivative this way until I get to a 0. And I have to integrate this way, so I have to integrate each time. So because that starts with a c, I have a negative, and it starts with an s, so it stays a negative. And we do substitution in our heads because we don't need to write all the substitutions out. And we know that this is a 1/3 and this is a 1/9. So there's your integral if you just connect the diagonals there. And so you have 20 times this, plug the numbers in, and you end up with this expression. And honestly, I didn't bother simplifying it any further. About the only thing I could have done is just get rid of the 0 because there's nothing I can really add when I start talking about the cosine of 6 radians or the sine of 3 radians and that sort of thing. So that is our answer right here at the bottom. Alright, so that still is method 1. So I guess I didn't cut off at quite the right spot. Oh well. But I didn't lose it. That's the good thing. Alright, here's method 2. Method 2 is going to be a situation where when you look, they give you dx or dy or something like that. Okay? So it's different. They don't give you a ds. They don't give you just the general curve and all of that. So this is going to require a tad bit of a difference here in terms of what you do. Okay, so we're going to have to find the parametrization for the arc that is going to be x equals e to the y from the point 1, 0 and e comma 1. So what I did to help you visualize, because it's always nice to graph, that I went ahead and rewrote this equation as y equals the natural log of x. And you know that if you're going to talk about a 0 to a 1, if you plug a 0 into this, well, that's not true. You don't plug a 0 into that. You plug a 0 into this, you get x equals a e to the 0, which is a 1. And you get a 0 for that, so that gives you the point 1, 0 right there. And if you plug in a 1 into this one, that's going to give you the point that is going to be e to the first, comma 1. So this point is e, comma 1. So what we're going to do differently here then is we're going to substitute in place of our x and our y, and we know what x and y is, it's right here. And so I'm literally going to just follow this, and I'll have x, which is the e to the t. So there's my e to the t. And then I have e to the y, which is going to be another e to the t once I plug it in. And then the dx. Well, what in the world is the dx? Well, if I take the derivative of my substitution right there, boy, I love substitution, I'm going to have e to the t dt. And so I substitute for that. There is no dy, so even though I took the derivative of it, it has no place that we're going to use in this whole process. Okay, and we figured out that our values for t would be 0 and 1 here. How did I figure that out? Let's see. If I put a 0, I get this point, and if I put a 1, I get this point. Oh, that's how I figured out that the boundary was 0 to 1. I just figured out what those numbers would be if I was going to get those particular locations right there. So I multiply it all out, and this is something you should be able to do in your head. 1/3 e to the 3t from 0 to 1, and when you get done with it all, here's your answer. There's method 2. Okay, I think method 2, I have a worksheet, because if I remember correctly, we did these in the Stewart calculus book when we used to teach out of that. And so I'm trying to make sure you are not taken by surprise by any way that the material is presented to you. You can evaluate these line integrals. So that's method 2, an example of that. Okay, another method 2. We're supposed to follow the curve that does 2 parts here. We have the part that is going to be this semicircle right here, and we have the part that's going to be this segment right here. So the curve, let's do that first. It's a semicircle. I remember from Calc 2, and I remember from vector valued functions because I studied it, and you studied it, yeah, right, that equation for that top half of the semicircle is going to be x equals cosine t and y equals sine of t, and it's going to go from 0 to pi to generate that thing. Oh, I don't remember. Well, you're supposed to square this, and you're supposed to square the other one, and it doesn't want to write there, and so you add them together, and we get our favorite identity, which is a 1, and there you go. That's the equation of a circle. And if we want the top half, put a 0 in there, that gives me a 1. Put a 0 in there, that gives me a 0. That gives me this point. I put pi in there, that will give me this point. So, all of you lazy bums that didn't do parametric, ha! I told you. So, here we have this integration symbol with that little c there, which is a line integral over the curve indicated by whatever the heck they're talking about. And we have to plug in our x and our y, but we also have to take the derivatives, which I did right here, of x and y. And so I'm going to substitute the x here, and so I have the sine of the cosine of t. And then I have dx, which is going to be this negative sine of t dt right here. Then I have the cosine of y, which is the cosine of the sine of t. Then I have my dy, which is going to be this cosine of t dt. I'm literally just following the substitution of that based upon my curve. Don't need to do any kind of magnitudes, don't need to do arc length. It's all done and taken care of it for us. And so I integrated all of these things. Okay, I had to integrate this by substitution. Too many red marks here. Go away. So if I do this by substitution, I would let u be equal to this part right here, and that would take care of the thing that I need to substitute for. And I would do the same thing here. I would let w be equal to the sine of t. That would take care of what I need to substitute for. And so I can integrate that. I don't need to do the substitution. I can do it in my head. If you need to do more, then show it. So I'm going to plug the boundaries in. And so when I plug that pi into this, I'm going to have a -1. And when I plug the 0 into this, okay, I'm going to end up with a +1 for that. If I plug a pi into this, that's going to be a 0. If I plug a 0 into this, that's going to be another 0. And these two things are zeros. And I'm left with a negative cosine of a -1. Well, I don't know if you remember your odd-even identities from trig. You're right. Cosine of a -x is equal to the cosine of x. So I didn't forget anything. I knew that that was the same thing as the cosine of 1, so why bother putting the extra negative in there? And so what ends up happening then is I can subtract these two, and I end up with this thing worked out to be a 0. So what in the world happened? Well, maybe part of this circle is above the xy plane, and another part is below, and so those little areas, you get a +1, you get a -1, and it adds out, it becomes 0. Does that still happen in 3 dimensions? Oh my goodness, yes. Absolutely it happens. All right, and then I have to do the same thing for the other curve. And I don't know how badly I want to talk about this. It's just a line segment. It's kind of the same thing we've talked about with line segments going from 0 to 1. I have to find the equation of the line, which we did here, using all our knowledge from chapter 12. And I substitute all those things in according to my dx and my dy, and my x and my y, and I get this expression. You know what? I think I'm just going to let you take a look at that, and I will count to 3. And so again, please note, I did say this, that the direct path from 1, 0 to -2, 3 gave a different result than what we did for the other, because that part is underneath a different part of the three-dimensional shape that's indicated by that equation, the equation that is basically right here, this one. And you can go back to the other in just a second. So I'm going to count to 3 for this, pause it. Okay, then I'm going to count to 3 for the whole thing, if you want to try to look at that whole thing. And I will count to 3 and you pause this. Alright, moving on. Again, method 2, there's a worksheet for that. Oh, here it is. Method 2, worksheet. And I think, like I said, I borrowed those questions out of the Stewart book because they presented things a little bit differently and has all the answers there. So that's on Canvas, nothing else to talk about there. Alright, now let's see where I'm at with this one. This looks like method 1. It looks like what we talked about earlier at the first page. How did I get back to the first page in my notes? Oh well. But there are the steps. But this looks like method 1 to me here. Alright, I think I can move on. I'll count to 3 though in case you want to look at it again or copy anything. And I'm done. Yay! Stop recording.